Hello, hello, hello. There she is. There's Delilah. Hello, hello. Good evening. Good afternoon. Well, yes. Good night, Lila. Right. Got it. Okay. And hello, there's the Raymond. There's the Raymond. And there's the Michael. We're in the house. All right. This is like a totally all right. I almost feel like it almost feels like something other than a physics class. Awesome, awesome. Thank you guys. And Shen and oh, I'm sorry, the chat. Good afternoon, Louis. There's Mantra. See, we got this is like video quorum central. I love it. I appreciate it. And there's where is she? I'm not even gonna ask. Wait, that's gotta be a back. Okay, I'm not okay, not my business. Good afternoon, Luis. Good afternoon, Jadith. Good afternoon, Camille. Good afternoon, Joyce. Good afternoon, Tania. Hello, Samaya. Okay, who else did I miss? Shen, hello. Good afternoon, Danielle. All right. Is that, I think we're good. Yes, and there are some, okay. Good afternoon, Shen. Oh, yes. Thank you, Shen. Okay. And nice avatar. That's very, am I looking at it like this? Okay. Okay. So I haven't forgotten that there's still some things we have to go back to. We will at some, believe me, I haven't forgotten that we never went over homework 1A. We will do that also, that I was going to expand on questions 4 and 5 in homework 1B. This will all still happen, but I feel like we have like momentum now. We should just keep the momentum for right now and not confuse everybody, or confuse me. Um, so we're going to, yes, we're going to continue with where we are right now. Um, and where we are right now is technically, technically, I finished the last question of homework 1B yesterday. I mean, I got an answer. We got an answer. But there's still a lot to be. But as I warned you, sort of that question is what springboards us into the real material. And then you may have seen, those of you who handed in homework 2, it's homework 2, at least a lot, the whole first, it's long, as you saw. And the whole first section of homework 2 is like all kind of picking apart the pieces of this thing that we just established yesterday. And of course, it would have been very hard. It was very hard for you to try homework 2 if you hadn't seen anything about what we did yesterday, Monday. But even with what you saw, even with what we just went over at the end of Monday, homework 2 is still like maybe a little bit like, oh, I see how it's related now. I see where this is connected, but I'm still not quite sure what to do. All understood? Uh, we're understood. And today we're going to expand enough on the last question of homework 1B that we'll start showing how it relates to homework 2 and how this all relates to physics. You'll really see how it relates to physics when we go back and do homework 1A, not to confuse you further. But anyway, so we're going to transition from homework 1B to homework 2 today, now. If you handed in homework 2 at all on time, which is many, many of you, thank you. Like if you handed in, if you made a valiant attempt and I could see that you were doing the 5-step method and you did it on a separate document and you just, you formatted it correctly and so forth. If you did all that and you handed it in on time, then you've already received 36 out of the 45 points. You may not have, it's possible that you didn't even see any feedback. I understand that. The point is you got 36 out of the 45 points already for just the fact that you were like on time and all that. And that also signals me, like the fact that you have a score in there then means later when you update a draft or anything like that, like I know that you were one of the people that was on time. So the sky's the limit on your points, if that makes sense. So even if you didn't get any feedback, you're going to start to see, hopefully, the feedback in this following class, and the next class, you'll start to see, or maybe you already know that you handed in a bulk of what you could do, but you couldn't do certain parts. You may already know what it is that you still have to do, or not. You'll see it in the next couple of classes. At which point you revise, you hand it in, you get the rest of the 45 points. Again, just to repeat from yesterday, because I know these are all unusual policies. I know, and they're sort of confusing. But it's all in the name of getting you to do as much to learn how to do things on your own and revise them as you go. And it's to me to get back stuff as quickly as I can to you without getting caught in the weeds or falling behind. So therefore, if you already got 36 points, it doesn't mean that's it. It doesn't mean it means you're now the potential to get 45. So over the next couple of days, if it doesn't become totally evident to you what to do for the rest of the 45, then, and if you really think you did everything, just, or either way, just like re-upload it and say, I still don't know what I'm supposed to do here. And I'll look at it again, and either I'll say, oh, you're right, you're right, here's the rest of the 45 points, or I'll say, okay, now, if you still don't know, now that we've gone through class and all that, here's my comments. Okay, so again, unusual system, I know. But the point is, if you got 36, it means you're on the road to 45. If you didn't get a 36, yeah, that means you still can hand it in. You still should need to hand it in, and you still will get a lot of points. You just won't get all the points. Okay, I hope that's clear. So I'm moving on now. Hello, Nico. Hello. You can stop me at any time with questions. I want to. So what I'm technically doing now is even though we technically finished the last question of homework 1B yesterday, I want to expand on it further. I want to sort of slow it down, slightly review what we said yesterday, and show you how it leads us to other things. So here's where we were yesterday. I'm just going to change wait, is there, sorry, direct chat. Wait. Great question. I think great question in the direct chat. I'm not going to read the name, but I'm going to read the question because the question says, do we have to wait for me, to grade the homework before we revise it? To grade the homework. Wait, if grade means comment and do feedback, no. Like, that's kind of what I'm saying. That's kind of unusual. Like, if you got a number on the homework at all, and it's not it's not all the points. If you already could just tell, oh, I see, like, if for example, if you just didn't do the last 4 questions, and you know that, and I know that, that's why, and you already know that has to happen. You don't have to wait for my comments or for the next number to revise. You never do. If you already know there's something to revise and you want more points, just go for it and put up the new draft. It saves us both hassle. If that's what you're asking, totally the answer is no, you don't have to wait. And you don't even have to wait for the next class. Like, if you know there's something to do, just do it. If you learn it from the next class, do it from the next class. Is that your question? Maybe tell me in the direct chat, is that your question? Or are you asking, do you have to wait for me to put any kind of number on it before you revise it? If maybe put in okay, fair enough. And thank you. Thank you for responding. Okay. So in order to revise something, no, you don't have to. That's interesting. I'm wondering, in order to revise something, you don't have to wait for me to put a number on it. The only reason I'm pausing, like, you don't. I mean, the only thing that's confusing to me is I'm not sure. I don't think there is anything that's come in that I didn't put a number on. But if you put in something, and then even before I get to it, you realize you still need, like, you realize how you could improve it, I would say then, no, you don't have to wait for me, you can revise. I would say, though, in that case, take away, well, okay, the one thing that's confusing about this to me, if you put in something and you put it in on time, yeah, I guess so I'm contradicting myself. Sorry, I'm changing my mind. I'm just confused because I don't know that that's a situation for anybody yet. But if you put in something on time and somehow you haven't gotten any points for it at all yet, yeah, I would wait till you get some points for it, then revise it, because otherwise, if you revise it before I put any points, I think Google Classroom might make it look to me like you were late. I'm not sure, but I feel like that's a risk. And if you did it on time, you want it to be clear to me that you did it on time, even if I'm late in getting to it. So I guess I'm changing so yeah, I get. So, and maybe you can make clear in the direct chat. I mean, it's a very good question. It's sort of an unusual, I guess I don't know why but so maybe tell me more if I'm not answering your question, or we can, text about it later or something. But to everybody, yeah, I feel like if you put something in definitively on time, wait for affirmation of that. Wait to know that I know that you were totally on time, and get whatever points you get, and then do whatever revisions, because then you can get all the points. But if you snatch it back and you put in a revision before I even like acknowledge the fact that it was there, I feel like then it's going to look like it was late, I think. Can you just acknowledge to me in the direct chat if I am answering your question now? And the reason I'm confused again too is I feel you also might want to tell me in a text or an email. I think anybody that's handed in anything right now, I think everything is back, even if not with feedback. But I feel like every single thing that's come in has come back with points, I think. And if I'm wrong about that, I want to know that. Um, could, okay. It makes sense? Okay. Um, okay. Okay. Cool. But can I just ask, as long as we're on this, can you just tell me in the direct chat, like, is there something that, oh, okay. Right. All right. So, like, right. If it's a situation like I see, okay. Right. So let's go with that. If you submit something and you submitted it in time, but it was like 10 minutes before class, so I haven't seen it yet, then sure, just wait till I do something with it, even if it's just points without feedback. Yes, okay, good point. Bottom line with all of this, because I've been try something slightly different every year. I'm always trying to improve these things and streamline and balance between everything. And in some sense, just to be totally honest, I've come to the conclusion in recent years that for everybody's psychological well-being, it's actually more important that I keep up with you. I think on the whole, people are willing in the pinch to sacrifice personal feedback for immediate acknowledgement of basically how they did, and that they're getting their grade feedback and getting the feedback in a class. If in a pinch, I sacrifice personal direct feedback for the overall flow of everybody seeing that I'm seeing what they're doing. And believe me, even if I don't give you personal feedback, it means I'm still reading your stuff. I'm just not stopping to write, which is because in the past, basically, I wouldn't turn things back and I wouldn't put points on them until I did feedback and everything, and then that becomes too much of a clog for everybody. And by the time they get the feedback, it doesn't even help them any so whatever. So sometimes I sacrifice just giving you reading it and giving you points so that we're in a flow for thorough feedback. And I apologize for that, but that's just kind of my priority at this point. So anyway, these are good questions. I will move on in a second. Oh yeah. Right. Oh no. Okay. This is another. I'm glad everybody's asking. This is another direct chat question. Someone's saying like, I submitted mine, but it's not completed. Is that okay? I could still get full points after revising and re-uploading? Question mark. Or will it be points out since I was only able to answer 1 point out of 3? Fair question. I will maybe get more strict and we'll maybe get more rigid about that as the semester goes on. But no. Right. I assume first drafts are not necessarily complete. Like for it to be a substantial first draft, like yes, it has to be substantial. You have to show, like when I glance at it, even if it's quickly, I have to see like acknowledgement of question 1 and 5-step method and and stuff like that. Like I understand you're not going to get all the answers on a first draft. That's okay. Now I will tell you, as we go through the semester, more and more, the more you practice a 5-step method and the more you believe in it, the more you'll see that really my standard can and will be that every single question has to be addressed with the 5-step method. You should start trying to train yourself that way. Like even if you get to these last questions where you feel like in homework 2, like it starts with derivatives, which is what we're going to get to now. And then by the end, it's talking about like dot products and cross products. I fully know that many of you, if not most of you, have never seen a cross product in any class. I know that. Now, technically, it gives a definition right there. So, like, technically, the better you get at physics thinking, the more you would be comfortable just like using the definition that I just gave you and trying stuff. But I totally know it's outside the zone for a lot of you. But more and more, what you want to do, ideally, on a first draft is even that material that looks totally unfamiliar, you want to set up the question with a diagram of what it seems to be asking. Like in that case, like we had all those vectors pointing, so copy some version of that diagram or some piece of it with your hand. So just set up a diagram, write out what the question is in your words, and then say like what for step 3 GDP, even for those vectors that we haven't talked about at all. I gave you a definition in the sheet. So step 3 GDP would be like the definition of dot product or cross, even if you don't fully think you know what that means yet. And then so what I'm really saying, I guess, again, I'm slightly backtracking right now. Yes, when I look for a draft, I'm looking for substantial, honest, thorough step approach. I'm not looking for completion yet, but I am trying to encourage you subtly to realize that the point of the 5-step method is it allows you to start doing things that you don't think that you know how to do. And definitely I'm saying the goal ultimately is that you, even on an exam, you address every single question and get at least to like step 3. And by the time you get to step 3, you'll see that you could set up step 4. You'll see that you know much more about things than you think if you just start applying the step method. So more and more I'll be looking for, oh, every question's got to be addressed. But will you have a final correct answer for every question? No. Okay, so, okay, long answer. Oh, wait. Oh, okay, cool. All right, great. Thank you, and submit for points. But yeah, like, okay, I know I'm like babbling, but really, honestly, I just want to remind you again, okay, look, I chose to be a physics major in undergrad. I know that. Like none of you, even though you're all choosing me in this class, I understand the class is like required, like you're all choosing to be scientists. Bless you for that. And really, the country blesses you and thanks you for that. I'm not kidding. But I know you didn't like choose to be, or many of you are not choosing to be physicists. I understand that. I chose, somehow part of me thought I liked physics or something and wanted to be doing it all the time or something. Okay. So I took a million physics classes in undergrad, and then I went to graduate school for physics, and then I went to graduate school again. I'm not saying that, well, I am sort of post, but like, yay. But what I'm really saying is, even with all of that, I need to make it clear to you. One of the reasons I'm still very excited to teach and all that is, even with me choosing to be a physics person 3 times, the number of times that some professor gave me a homework assignment or an exam, and I looked at it and I was like, WTF to the 3rd power? Like, what? Like, don't think this stuff is easy for me. And I'm not saying that for sympathy, but and every physicist, like, they get to a level where they're doing stuff that is really hard. And when I was studying all this stuff, I all the time had the experience. It was stressful. It didn't come easily at all. I liked it, so that helps, but I didn't like doing badly, and I did a lot. So I would look at exams and homeworks, and I literally would say exactly what I think a lot of you say a lot of times, even when you're looking at my homework, or even when you looked at homework too. I would say the same thing, like, I have no freaking idea what you're even asking me. Like, believe me, that is not because you don't belong in this class, and don't think that people that do physics don't feel that way. I did and I do. The thing that I learned in college and in graduate school, and in graduate school again, the thing I learned above all, or at least the thing I got better and better at, or got more courageous at trying, is what to do when I don't know what to do. And that, I promise you, whether you're going on a physics or any form of scientific research that you're all going into, what you really want to learn, if you're doing original research, you're necessarily doing something that no one's done before, let alone you. So what we're really here to learn is how to do stuff that we don't know how to do. And that means, even for some of you, homework 2 already feels that way. I'm not doing it to make you feel bad. I'm doing it to help you learn how to feel better with that. And so the answer is the step method, or some version of it. The answer is break things down into tiny little steps, and don't think that you have to see the light at the end of the tunnel before you start walking into it. The biggest mistake that smart, successful people make, when they get used to being smart and they get used to being successful and they get used to things occurring to them faster than their peers or our peers, is that we start not getting used to what it feels like to not know right away what to do. And we think if we don't right away know what to do, then all hope is lost. Not the case. You don't have to right away know what to do in order to start doing it. Long story. Okay, you all get it, I'm sure. Okay, so no problem. No problem, direct chat person. Okay, you just missed the best, most inspirational speech ever. How could you miss that speech? I'm just kidding. Okay, so back to homework 1B. Here's what I think. I'm just changing the view on the screen, pardon me. Okay. I think in homework 1B at the end, what we kind of concluded was that if something is oscillating, if an object is going back and forth cyclically, and that's oscillation, if you want to put in your notes, oscillation means cyclical motion. Excuse me. means cyclical motion. If something is oscillating according to the equation F equals negative kx, in other words, if the thing oscillating is governed by Hooke's law, by some version of elasticity, if it's then we can, so if physically something is obeying Hooke's law, then mathematically, if we apply Newton's second law, we can rearrange things and realize that the mathematical description of something going back and forth, back and forth, back and forth is what we will now from here on in call a differential equation. In fact, technically, this is a second order differential equation. Why second? Why second order? Because it's a second derivative. I mean, that's straightforward. It's a second order differential equation because on the left side, we're presenting a second derivative. And it's a differential equation. We call it a differential equation, like not just an equation with a derivative in it, but it's called a differential equation, we said yesterday, Monday, because the second derivative is being expressed as a function of the dependent variable, not the independent variable. Sounds like mumbo jumbo, but it's a huge fundamental distinction. We're saying that the rate of change of the rate of change of x with respect to t seems to depend on x. If it depended on t, it would be straightforward. Like rates of change, like a equals v minus v naught over t from, well, actually I don't want to get all, whatever. Like if a rate at which something changed with respect to time depended on time, then we would just sort of unpack that derivative. We would do that derivative backwards. We would do a thing that you know is called an integral. We would do an antiderivative, which we can figure out through using an integral, and we'd be okay. But this is not that. This is saying that the rate at which x changes, or the rate at which x changes with respect to the rate at which x changes with respect to time, doesn't depend on time. It depends on x itself. If that sounds at all circular or all feedbacky to you, you're correct. That's why it's a special kind of funky relationship that we call a differential equation. It cannot just be solved like just by some procedure. There's all kinds of differential equations. They're solved by all different types of techniques that we learn from experience. They are not solved forward, they're solved backwards. So from experience, and one technique for solving this type of differential equation is to conjecture and verify. Like whether you're in a math class or, thank you. Sorry, I just saw the chat. I appreciate that. I appreciate you appreciating it. Totally open up a portal for making me feel good. Thank you. Okay. Boy, no better way to distract a professor than compliment. Okay, you can't solve differential equations forward ever. Many differential equations can't be solved at all. Some can, we know from experience how we tried certain things. We conjectured certain things from either from our mathematical experience or from our scientific lab experience or both. We conjecture certain things and then we test them. And if they work, if they satisfy the test, then they're correct. It's the test that makes them mathematically precise. It's the guessing and conjecturing that comes from scientific or mathematical experience. And again, let me just reinforce that when I say guess and check or conjecture and verify, that's not just for you guys because you've never seen this before or something. And it's not just for scientists because scientists cheat at math. No, that's the way a mathematician would do it also, these kind of differential equations. They would, or they would, and then they would the first time anyway, and then they would just get used to knowing the solution and just know it. But this is the real way to go, and we happen to have the benefit of scientific lab experience, so it helps our guess. So what we said yesterday was, that our guess is some kind of cosine function. And we guessed that because we pictured what the lab data would look like if a spring was going back, if a mass was going back and forth on a spring, and we put its position on the y-axis, we put its time on the x-axis, like the mass would be going back and forth and back. I mean, it's just going back. You understand, in space, it's just going like this, or just going like this in space. But once we put it on a graph and our x-axis is time, then, it smoothly makes a cosine graph picture. So we guessed we guessed that the function that would describe where the mass is at any time is a cosine picture. But then we said that's not good. That's huge. So the type of function we guessed is cosine. But we also realized that's not good enough. It has to be more precise than that. Units of measurement alone, which is a very helpful reference point for scientists, the unit measurements alone don't work if you just write x equals cosine t. Like literally, they don't work. You can't take the cosine of a second and have it spit out a meter, which is what would be the case if you just wrote x equals cosine of t. So we thought, wait, we got to put some things in there to make the constants work. I mean, excuse me, we got to put some constants in there to make the units work. And again, you might think, well, that seems like sort of, we're just trying to construct a guess. We're not going to believe the guess until we can test it, but we constructed a guess. And we said, okay, if we put, well, I'll go to the left to right this time. We said, first of all, this whole answer has to spit at the whole right side of the function. I'm talking about the bottom line of the board right now. X equals x naught cosine omega t. I'm saying as of yesterday, we were guessing that that was a solution. Oh, sorry, is the board cut off? Okay, solution. We were guessing that as a solution. Now I'm ultimately saying it is a solution, but first of all, we just guessed it. We guessed cosine because we just pictured the motion is periodic. It's going back and forth. Then we guessed that based on units, there have to be some constants thrown in there around the variables. So to the left of the cosine, we put x naught. That was a guess, but where did it come from? It come from saying, look, at the end of the day, cosine itself, no matter what you're taking cosine of, cosine is going to spit out a value between 1 and -1. And it's literally just going to be a dimensionless number between 1 and -1, right? So that's not what we want. We want x. We want a position. Like we're talking about the mass on the spring. It's going back and forth between positions on a meter stick. So first of all, our ultimate answer for x shouldn't just be a number. It's got to be a number of meters. And second of all, it can't just range from what, like, it can't be the case that we're only allowed to have the mass go back and forth between 1 meter and -1 meters around the equilibrium position. So we said, wait a minute. What if we put its initial value right before the cosine? What if we guess that the entire cosine thing, like that the clock will tick and each tick of the clock will generate like a cosine value? And then what if that value is multiplied by the number 0.15 meters, right? I mean, in the case of our homework, like what if it's multiplied by the initial value of the mass, the initial position of the mass as measured in meters? So in our homework, that was 0.15 meters, but in general, that's x naught, the initial position, right? So if we multiply cosine by x naught, that's like scaling up the entire function, right? It's literally like you learned this in some other class, like it's like taking the entire cosine thing and stretching it so that it doesn't just range from 1 to -1. It ranges from 0.5 to -0.15 to -0.15, right? And I hope that's clear. And stop me if that's not clear. Like, again, that's why we guess that x naught has to be before the cosine, because then take it to the limiting case in your mind. Take the extreme argument. Then if you plug in 0 for t, if we're asking where is the mass right at the beginning of this experiment, where is the mass at t equals 0? Well, t apparently is being multiplied by some weird thing omega, which I'm next going to talk about, but t is multiplied by some constant. So if you plug in 0, multiply by a constant, even if I don't know what that constant means, if I multiply 0 by a constant, I get 0. Then I take a cosine of 0, I get 1. And then I multiply 1 by x naught. So at time equals 0, it would spit out x naught. It would spit out 0.15 meters as a value for x. Like that's what we want. You see what I'm saying? And anywhere else, I hope you see what I'm saying. That's so we stretch the whole cosine graph by the initial value, what turns out to be the maximum value, and it turns the raw number into a displacement measured in meters. So that's why I guessed that there had to be an x naught before the cosine omega t. Now I make a similar argument for omega, but now this gets a little bit more, wait, I'm just going to actually, just really quickly, can you just raise your electronic hand if that makes sense so far, honestly? Or cool. All right, cool. Thank you, Lila. And one person. Okay, I thought two. Okay, thank you. All right, raise your hand if you know that this is the moment where you're supposed to raise your hand. Okay. All right. Cool. Thank you. All right. So now I believe you. I totally believe you. Um. Do you believe me? So that's the X naught. Now I'm going to apply the same type of logic to the omega. And I know I did this yesterday, but now I'm trying to expand, slightly review, slightly slow, like refresh it, or but I'll also expand. So omega, that thing before the T is not a W. I mean, it's a lowercase Greek letter omega, and I put it there before the T for the similar type of reasoning that there's got to be. Oh my goodness. Hold on 1 second. All right, we might be interrupted for. Okay, I'm slightly surprised at some. Okay, anyway, we might be interrupted for a minute in a minute, but the omega is put next to the T for same reasoning that units that we have to adjust the T with a constant to make the units work out properly, like what I was saying before. So we put in this omega that first of all, don't get confused by the fact that it's a Greek letter. It just happens to be a Greek letter because it turns out to be like very important in physics in general. But right now it's just a letter that just stands for a constant. Pardon me for 1 second. A constant. Okay. Okay.
Yeah, I'll tell you in a second.
Okay. Okay, so omega is just a letter that stands for some quantity that does not change throughout the problem, like a constant, that apparently must be measured in radians per second for the equation to work at all. Well, so but what do I mean radians per second? Okay. Radians per second is some kind of rate. Like meters per second is a rate of velocity, right? Like meters per second is how quickly you're traversing meters of space through seconds of time. Well, so radians per second is also some kind of rate, but radians are units or are measurements not of space but of angles. So this is some kind of rate at which you're like something is moving through angles. So we call it angular frequency. So from now, one thing I'm just declaring as like knowledge in this class is from now on, omega, whatever it is something that must be measured in radians per second. So we're going to call it angular frequency. We could have called it, you could call it angular velocity, and there even is a thing called angular velocity, and it's very related, but you'll see shortly why we call it angular frequency. It's an angular rate. But two questions come to mind. First of all, like, okay, what is a radian? Like a lot of us, I know you, and we have to use radians from now on. We're not going to be using degrees. We use radians in physics, and I know you've learned about them in math, but I also know if you're like me or like many people, you may have used them a lot, but you still might not be 100% comfortable with them, with radians, I mean. Radians are a measurement of an angle. But now what I want to say is, if you're not totally comfortable with radians, it's possible it's because you have a slight it's easy to not actually understand what an angle is. So I want to take a moment to explain what an angle is, and hopefully help with what a radian is, a moment to do that. But more particularly, even if you do know what an angle is, and even if you do think you know what a radian has to do with angles, what you very legitimately might be thinking is, fine, like radians, angles, yes, I remember it from trigonometry, like angles are measured in radians, sure, but like what in quark's name does radians and angles have anything to do with this situation? Like I thought a mass was just going back and forth, straight back and forth on a tabletop on a horizontal axis. Like why are angles coming into this all of a sudden? Good question. So here's the deal. Let me remind you that even though people think of angles often, when you think of an angle, you might think of like how far apart two lines are, like two lines that meet in a corner. And I'm not saying that's wrong, but it's deceptive. It's misleading. When you picture these two lines, like a vertex or between two diverging lines or line segments or whatever, what you're really supposed to be picturing is a section of a circle. In fact, specifically a fraction of a circle. What an angle is a fraction of a circle. When we measure the size of an angle, when we say that one angle is bigger than another angle, we're saying that one angle takes up a larger fraction of a circle than another angle. And let me dwell on that for a minute. That's not a technical, I mean, it is a technical, but that's not like a side point. Like, if you think, and right now what I'm saying is we know what angles are, and we compare the sizes to angles, regardless of whether you think you're comfortable in degrees, or you think you're comfortable in radians, or you think you're comfortable in English. Let's get it straight. Everybody in this room knows what this angle is. Right? I mean, like, and everybody in history has had some kind of special name or something for this angle, like the right angle, right? Like whether you call it a right angle or you call it 90 degrees or you call it pi over 2 radians, everybody can recognize this angle when they see it. And the Greeks did tons, the ancient Greeks did tons with it and stuff like that. But what is it that you're recognizing when you see it? I mean, it's hard, like you can say, oh, well, it's like when they're like straight and they're not, like one's horizontal and one's vertical. But I mean, I could bend it like this and it's still right, even if neither is like everybody knows it. But what is it? What is it that we're recognizing? Notice this, whatever this right angle is that everybody knows what it is, notice you can recognize it no matter how big my hands are. It doesn't have anything to do with how long this, you don't even know if I'm asking you to look toward my elbow or just toward my sleeve. Like, right, it's hard when I'm backwards. This is a right, what is my problem? Whatever, you know what I'm saying. This is a right angle, regardless of how long my fingers are. And the regardless of how long my fingers are is the key to the whole thing. This is a right angle because it's a quarter of a circle, regardless of how big the circle is. That's the point, right? The Greeks called it a quarter of a circle. Like literally, they didn't even call it 90 degrees. They did math with it and they just called it a quarter of a circle. It's a quarter of a circle. And the thing about circles is that you can talk about sections of them regardless of how big they are. That's the thing about circles. The thing about circles is, as you know, the circumference of a circle, of any circle, you know, is this crazy number pi times 2 times the radius of that circle. Or in other words, the circumference of any circle is pi times diameter. Now, pi is as exciting as you think it is, but maybe not for all the reasons that you think, or maybe for more reasons than you think. The thing about pi is it doesn't matter whether it's 3.1415, like it doesn't matter how many digits you know it to. It doesn't matter that the Greeks didn't have digits, like literally, they didn't have a base 10 system. You ever hear of Roman numerals? Romans came after the Greeks, right? Roman numerals. You ever think about this? You know what numeral, like many of you know, like I is Roman numeral for 1, right? And like V is 5, etc. Have you ever noticed or thought about the fact that there's no Roman numeral for 0? There is no 0 back then. Like I'm getting off on a tear, but just note for a minute, 0 is not established to be a number as part of any numbering or counting or mathematical system until the thank you, Abdul. And funny, okay, thank you for acknowledging. And let me say that it wasn't until the Islamic Empire, until the Middle Ages. It was Muslims, and I mean this dead seriously and with total reverence. Like ancient Greeks did not invent or use 0. Ancient Romans did not use 0. Ancient Hebrews did not use 0. Like 0 got established as as part of an Indian and like as a Muslim tradition. And the whole numbering system and mathematics got revamped around it to the point where we now do base 10 and have place value and decimals and all that stuff. There was none of that until 0 was invented or discovered like a few hundred years ago. And yet all this math, Pythagorean theorem, all the stuff you learn in trigonometry, well, certainly all the stuff you learn in geometry and all that was all done successfully without even a 0. Okay, that's a sidebar, but it is fascinating. So what I'm saying is the Greeks didn't say that pi was 3.1415. They didn't have a point to say that. Oh, well, really good question. But the quick answer is because it turns out that if you're quantifying things, well, basically the simple answer is as a placeholder. Once you invent this idea of place value, which didn't exist until the like Middle Ages, once you decide to do place value, once you group numbers in powers of something, we do powers of 10, right? And start organizing numbers that way, which totally expands our ability to navigate numbers and do math and all that. Once you do place value, you have to have a symbol to occupy a place, even if there's no units occupying that place. Like once you have, it's a placeholder. I mean, it's the simplest answer. I mean, and it's a fascinating topic, but we don't start counting nothing as something until we're organizing everything into groups. Like, so the number 11 is one group of 10 plus one group of one, right? No one thought of numbers that way until they did. And once they did, then you had to be able to say things like 101, which means one group of 100, 0 groups of 10, one group of one. So you have to mark, like you have to account for the groups for each group once you're grouping things in places. So there has to be a placeholder that means none of that group. It doesn't mean nothing, nothing, nothing. It means none of that group. Anyway, that's a lot, but great question. And I hope that sort of answers it, at least for the moment. I'm happy to talk about this in off, outside of class too, as you can see. But okay, I'm getting crazy. My point is, the significance of pi is not its decimal expansion. That's not the significance. The significance is the fact that it's constant. The significance is the fact that no matter what circle you pick, whether you pick like a lens of my glasses or you pick a tree trunk, that if you tie a string through a tree trunk, like literally like cut through the tree trunk from one end to the other, i.e. a diameter, and put a string down on the ground that represents that diameter. And then you take another string and wrap it once around the tree and put that string down on the ground. It doesn't matter how big that tree is, or it doesn't matter if it wasn't a tree and it was like a tire of your car. No matter what, if you put those two strings down and compare the length of going around to going straight across, the comparison is always the same. It's always a little bit, one string, the circumference string is always a little bit more than 3 times greater than the other. That's phenomenal. That's the issue, is that there's a ratio between circumference and diameter that seems to hold up no matter how big the circumference is. That circles have that perfection, that they're just always to that scale. Therefore, a fraction of a circle is a universal idea. A quarter of a circle is instantly recognizable, and a half of a circle or a full circle, they're all instantly recognizable as a certain portion, regardless of how big the circle is. So an angle, what an angle is how far along you go, like the edge of the circle, per how big that circle is. Like an angle basically just is how far along the rim of the circle you went. But then we divide by the radius to say, look, if you went 2 meters along the rim and I went 1 meter, that doesn't necessarily mean that your angle is twice as big as mine. It might just mean that your circle to begin with was twice as big as mine. So if we just divide by the radius, what we're saying is, like for any circle at all, the ratio of how far you went out per how far you go over, that ratio is always the same. I don't know if that, in other words, yeah, like if you go 3 times farther than you went out, you went around the whole circle. If you go 1.5 times around, you went half the circle. That's always the same. So an angle is literally a pure fraction. Like its arc length per radius, i.e. the meters, you may or may not have ever noticed this, cancel out. So an angle really purely, oh my goodness. Okay, hold on. This is the interruption now. Hang on 1 second. I'm gonna pause. You okay? You're sick?
What?
Oh, you just come in? Oh, you're not going to work? Oh, okay.
No.
Oh, just hi. Okay. Hi.
Hi.
Hi. I'd love to see you. I love you. Okay. Okay.
When are you gonna be done your Zoom?
In 30 minutes. Are you then?
Sure.
Okay. Are you going to horses?
No.
Oh, so that's okay. 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 Sorry. I have a family. Sorry, and the family includes a dog that is about to come in, which shouldn't happen. Okay. So angle is pure ratio of arc length to radius, pure ratio of meters to meters. So truly speaking, an angle is dimensionless. It's just a fraction. What an angle, literally a fraction. It's a fraction of of a circle, with the idea that no matter how big the circle is, the fraction still has universal recognizability. Specifically, you know that the circumference of a full circle is 2 pi times r. Therefore, say you go around the entire circle. If you go around the full circle, you go around 2 pi r, and according to the definition, I'm just applying this definition up here. According to definition, you divide by r. So to go around a full circle is 2 pi radians. Here, now suddenly I just said radians, and you might say, wait, I thought you were going to explain radians. Now you're just using, no, this is the explanation. I'm saying a radian is the thing such that 2 pi of it brings you around a full circle. Radian is just word for pure measurement of angle. It's not even strictly speaking a unit, to be honest. Neither are degrees, because strictly speaking, angles don't strictly speaking have units. They're dimensionless. But radian is the word we use to connote angle. So we're saying if you go around a full circle, so we're measuring all of our angles in ratios of arc length to radius. So if you go around a full circle, that ratio is 2 pi. We're going to call it from now on 2 pi radians. I'm literally saying a radian is the thing such that 2 pi of them brings you around a full circle. And a full circle is an angle, right? You may think of a full circle as a 360 no scope, as my son does. But that's just because you got habituated that, like, you can recognize a full circle. And my son can recognize a full circle. He knows a full circle is 360, and he can recognize it no matter how big the person is doing it. And from that, he's in 4th grade. He knows then that a half circle is 180, just because, right? He can picture that. But it's not like 360 literally makes sense. He's just gotten habituated to hearing that. And similarly, oh wait, sorry. Right. Oh, so Raymond, exactly. No, yeah, I'm with you. Right. That's what I'm saying. I'm literally saying then 2 pi radians means 360 no scope. Forget the no scope. Obviously, that's like a ridiculous Fortnite reference. But I'm saying 2 pi radians literally means the same thing as 360 degrees. Only what I'm actually saying now is you could see the logic of where 2 pi actually came from if you think about it this way. Whereas 360 just came from you memorizing it because someone told you. There is a reason for it, but the reason doesn't help you on paper with math at all. There's a historical reason for it. But so 2 pi radians is a full circle. Therefore, pi radians is a half circle. Pi over 2 radians is a quarter circle. And now, if you want to then say in the end, so what the heck is a radian? So what is a radian? Well, round, approximate in your mind. 2 pi is roughly 6. It's 6.28, whatever. 2 pi is roughly 6. So what a radian really is, a radian is a fraction of a circle. That's all it is a fraction of a circle. How big of a fraction? Approximately a sixth. Why? Where did I get a sixth? Because 2 pi radians makes up a full circle. In other words, about 6.28 radians makes up a full circle. Rounding, essentially 6 radians make a circle. So what a radian is a sixth of a circle. You should think about it that way from now. Well, I would advise that you think about, I'm approximating just, but so you can picture it, so you have a sense. A radian is like if you divided a circle into approximately 6 equal triangles. Each of them would be what you might call about 60 degrees. Technically, it's a little bit lower. It's like 57. But basically, if you divided a circle into 6 pieces, each of those pieces, regardless of how big the circle is, each of those pieces would be a radian. Now, what does that have to do with masses going back and forth on springs? Well, the answer is that we have all this knowledge of circles, and circles are the same, like have this same built-in ratio no matter what size they are. That's math. Physics, what we're looking at now is cycles. And cycles have that same feature, that a cycle doesn't have to have a particular size. Like a mass can go back and forth from 0.15 to negative 0.15, or back and forth from 0.3 to negative point, whatever. Or a cycle could be in a washing machine. Like a cycle does not definitively mean a certain size. But we have all this knowledge of what happens in cycles. We know consistent things can happen in cycles once it's a consistent cycle. So what we do is take the mathematics of circles and graft with a T. We borrow the mathematics of circles and use the mathematics of circles to explain the physics of cycles. Specifically, we use cosines of angles to describe cosines of angles in an oscillating system. Where's the angle? Angle is a section in an oscillating physical system. By angle or by radian, we mean a sixth of a cycle. I'm just looking at the chat. Okay, we're talking about oscillating systems now. Oh yes, absolutely. Thank you. And but direct chat person asked me to repeat and definitely submit that for points for please go back. Yes, the last thing I just said, I think it's what I just wrote here, but I think what I last said was, well, why suddenly we're talking about radians in physics class and why we're talking about cosines is we're talking about angles. Why are we talking about angles in something that's going back and forth in a straight line like this? The reason is because something that's going back and forth like this is moving in cycles. And what I'm claiming here is that we can take the strict mathematics that we already have for circles and impose them onto the physics of cycles. So in the end of the day, if an angle is a fraction of a circle, then at the end of the day, for us, a radian, and if it's measured in radians, then a radian, I think this is the last thing I just said. From here on in, a radian in a physics class, a radian is a fraction or a section, a piece of a cycle. Specifically, a radian from now on means approximately a sixth of a cycle. I say really, technically, it's 1/2 pi, but just so you can feel what I'm saying, what a radian is a sixth of a cycle. A radian is that thing where if you do 6 of them, you've done a full cycle. What do I mean by a cycle? I mean there and back. So a radian is like a third of the way there, and then like another one, and then you get there, and then you're coming back a third and a third. And I don't know. So I didn't say it exactly the way I just said it, but that's what I'm trying to say. Like a radian is approximately a sixth of a cycle. So when we say, when we say, and is that okay, direct chat person? Like, did you catch it? I mean, or you can let me know if, but when we, oh, and also sidebar, whenever I use square brackets like this in the notes, if I use, oh, great, thank you. Okay, and that's more points you should submit. Great. Okay, thank you. Whenever I use square brackets in notes, I mean specifically to be looking at the units of whatever is in the square brackets. So like I'm when I say here, so like omega is not defined as radians per second, it's defined as angular frequency, but it's measured, I'm saying with these square brackets, omega is always measured in radians per second. So what that means here, so so like if omega is 3 radians per second, in effect, we're saying this thing is going back and forth at 3 cycle sixths per second, 3/6 of a cycle per second, or in other words, a half a cycle per second. So it means it's going like there, Mississippi, back, Mississippi, there, Mississippi, back. Now I'm going to write that more precisely in a second, but I'm just trying to give you a feel for like why is omega coming into play? Like, what does that have to do with anything? It's omega is a frequency. That's why. So do you see why they call it angular frequency? It's how frequently cycles are occurring. The only thing is it's scaled in a funny way. In fact, let me be so very specifically, and please understand, every time I say sixth, I'm rounding on purpose, just so you can picture what I'm talking about. Exactly speaking, omega is not a sixth of a cycle. Exactly, it's a 1/2 pith, if that makes sense. But that's like so awkward to say. So, okay, but if you want the precision now, here's the precision. I'm saying um I'm trying to make this real, so say you're sort of what I'm trying to ask you to look at now. I'm saying in physics here, we're looking at an oscillating system. We're looking at something that's going back and forth cycling. So what I'm trying to say is the largest way to describe this thing is with a cosine, like it's going back and forth, just like a cosine function. But specifically, like a constant that clearly, I think, would characterize the motion of something going back and forth, like something you'd want to know about it, something that could even be a constant descriptive feature of it would be how quickly, how rapidly it's going back and forth, right? Now, not quickly like velocity, not how quickly is it going through space and meters, because in fact, as we already established in homework 1B, that's changing every single moment, right? It's going slow, then it's going fast, then it's going slow again. So velocity is not like a constant feature of cyclical motion, and neither is acceleration, and neither is jerk, and neither is any such derivative with respect to time. But there is something constant about this thing going back and forth. It's going back and forth a certain number of times per second. Now I'm saying mathematically, the most direct way to track that is through this thing called omega. By mathematically, because we already know so much about circles and cosines already apply to circles, the most direct way to track what's going back and forth, I mean, the rate at which it's going back and forth, is to talk about radians per second, i.e. cycle 6 per second. That's what I'm saying so far. But then you might say, or people would say, well, that's very mathematical. I guess I get the mathematics, but like, come on, like if we're just like looking at a thing going back and forth, like, can we get rid of this like sixth business? Can we just like talk about like how frequently, like it's just like how many cycles per second is it making? You might say, fair question. And there's a name for that. That's called standard frequency, not angular frequency, just standard frequency, normal everyday frequency, like how, and it's abbreviated with an F. And in many textbooks and websites, it's abbreviated with the lowercase Greek letter nu. If you're looking this stuff up in a textbook or on a website, or even, I can't remember Khan Academy, how they do it, but often if you see the lowercase Greek letter nu, that they're talking about this, or in PChem, I think in instrumental, they use nu. Anyway, what is that? What is standard frequency? It's just exactly what you would want, your intuition would want. It's how many cycles you complete per second. And we even have a name for that unit. A cycle per second is called a hertz. Like a hertz. I mean, that's a hertz. So like radio stations like 95.9 megahertz literally means something is oscillating or vibrating at 95.9 million cycles per second. And that's why it's called FM, because it's frequency modulation, and modulate is to change. So can we talk about things just in normal frequency without getting involved in the angle stuff? Yes, we can. But understand that the conversion factor is just the 2 pi that I'm talking about. In other words, like you can that's an equation you can memorize or whatever. Like it's always true. It's really a definition. I'm just saying, so from now on, in order to understand, or you can reiterate whatever way you, if I'm trying to help you understand what omega is, because omega is a big deal. Oh, sorry, that should not be screwed. So I'm saying from now on, you could go back and forth if you're trying to relate to omega. If I say the omega of this oscillator, if I say the angular frequency of this oscillator is 4 pi radians per second. If I say that it's 4 pi radians per second, that sounds very obscure, even to me. I mean, it's a mouthful. If you hear omega equals 4 pi radians per second, you might not immediately relate to that meaning anything in the physical world. But what I'm trying to say here is, hold on, just divide that by 2 pi. Like radians per second is how many radians we're doing. If you really, it's related to, a radian is a portion of a cycle. So if you want to relate this to cycles, just divide it by 2 pi. If I say the thing has an angular frequency of 4 pi radians per second, that's, since there's 2 pi radians in every cycle, that just means it's doing 2 cycles per second, literally. Something that has an angular frequency of 4 pi radians per second is going there and back twice every second. That's all that means. And go back and forth, whichever. So frequency is a little bit more physically intuitive, perhaps, than angular frequency. But angular frequency is more mathematically accessible and precise, accessible to our equations. Lastly, if you want to relate to it even better, if you want to go all the way back to what you actually could measure or observe in your first lab and your second lab, there's this concept called, oh, sorry. There's this concept called period, right? First lab. Period period is the reverse or the inverse. Period, the period of an oscillator is how much time it takes to do cycles. Literally, it's how many seconds it takes the oscillator to do each one cycle, right? So as opposed to cycles per second, it's seconds per cycle. So what is then if and why do we care about that? Because that's the easiest to picture in our mind and to measure in a lab, like just as you did in lab 1. Like you start your stopwatch when, like, so you let the mass start going back and forth for a while, and you start your stopwatch as soon as the mass is at an endpoint, and you just let it go like 20 cycles, and you look at your stopwatch and you divide the stopwatch value by 20. So you've now decided, like, it's straightforward and you can see what's happening. It's how much time it takes each cycle to occur. And in the end of the day, that is just the reciprocal of standard frequency. So I'm saying now, we have 3 things. We have 12 minutes. What I've been trying to do for the last many minutes is give you some perspective on what omega means. Because from here on in, we're saying, given a certain differential equation, the solution to that differential equation, given the differential equation that describes this kind of oscillation, the solution to that differential equation is x equals x naught cosine omega t. I think the omega is the hook behind that. First of all, it's like the newest thing. Second of all, it might be the most intimidating thing in there. And it ends up being sort of like the super most important or driving thing for all the rest of our topics. So omega is angular frequency. Angular frequency is related to standard frequency by just dividing by 2 pi. Standard frequency is related to period by just flipping it over. These three things, angular frequency, standard frequency, and period, are three distinct ways to just measure the rate of oscillation, the apparent constant rate of oscillation of any oscillator. They're interchangeable. If you know one, you automatically know the other two. If you understand one, you can translate automatically back and forth between the other two. They're all describing this, like literally, if you know standard frequency, you multiply by 2 pi, you have angular frequency. If you take angular frequency and put it under this, then you have period, right? If you know one, if you can follow on what I'm talking about on any one, then you can literally get the other two. So there are three different ways to describe the same piece of information, which is the rate at which an oscillator is cycling. Why do we have all three? Because angular frequency is the one that most explicitly comes out of and feeds the math. Angular frequency is what we need to do all our analysis with cosines and all of that. We're taking angular frequency from all of our pre-existing knowledge of cosines, et cetera, that come from circles, and we're imposing that on an oscillating system. So omega is the most mathematically explicit and productive. Period is the most physically measurable and picturable for all of us. All of us can picture period more easily than the other two. Period is the picturable, measurable one. Angular frequency is the mathematically explicit one. Standard frequency is the bridge between the two. That's the deal with that. Having said all that, then we say, and what I'm about to do right now, I know we only have 9 minutes left. What I'm about to do right now largely is kind of repeat something I did yesterday. If you understood yesterday, then just relax and listen to this. Okay, I'm about to repeat something I said yesterday, but the reason I'm repeating it is to try to link it, try to help you see what's going on in homework 2. Like, I don't have time to drive through all the homework 2 exercises, but what homework 2, at least at the whole beginning, the derivative things, is all about this. So if you didn't catch what I said yesterday, catch it now. If you did, then just like relax and try to think, or then look at your homework too and think of this in the context of that. I'm saying we're saying that this differential equation, like this is the differential equation up here for this type of oscillation. This is the differential equation for oscillation that is governed by Hooke's law. We are saying if you know that Hooke's law is driving a system and therefore can be expressed with this differential equation, then the way to predict the system, like the way to know where the system is at any given moment in time is this cosine solution. We guessed it, we put it together from all these thoughts that I've just been trying to express. But the question is like, that's all a guess. Why do we actually believe this? Like, how did we test it? How do we prove that this guess actually works? What we did yesterday, we tested by differentiation, by taking derivatives. And that's what the homework is asking you to do, right? The homework is asking you to essentially, the homework is going back the other way. It's saying, imagine this function. Is it actually a solution to this differential equation? And at the beginning of the homework, it's literally giving the exact same example that I'm talking about right now, but maybe using different symbols. So it's saying like, remember, I'm proposing that this cosine function is a solution to that differential equation. How do we know that the cosine function solves or satisfies or fits the differential equation? Well, it satisfies it or fits it if it's true. If it's true that if it makes the equation true. If it's true that the second derivative of x with respect to time actually yields negative times k over m times x, then it's true. So what we did yesterday, I'm just going to quickly do again, because again, this is what you do in homework 2. If what we first take the first derivative of x above. Oh no, and okay, I'm doing this quickly again. We're gonna have to stop it. Well, I know for some of you, you need to refresh chain rule. Please do. Like, use this as an excuse or a moment, I mean, after class, to go refresh chain rule and go refresh your trigonometric derivatives. But it seems to me that if I apply both, the derivative of this would be, and again, for your step 3 GDP for a thing like this, you would literally write out if y equals f of x, and if y equals sine of x, then dy dx equals cosine of x. Like, just write that out. That's a GDP. And if, and write out the chain rule as a GDP, because that's what I'm basing this on. But anyway, so we said the first derivative is that, and then I took the second derivative because I'm supposed to be looking at second derivatives. So I took the second derivative and I got this from chain rule again. And the negative sign stays, right? The derivative of sine equals cosine, but the derivative of cosine equals negative sine. You know what I'm saying? So like, we popped in a negative sign in the first derivative, but then we don't pop it out on the second. So this is a derivative. Then the second derivative. So then we said we can rearrange and say it equals. Oh no, it equals that, right? So then we could say, but that whole thing supposedly is x. Therefore, apparently, dt this equals this, right? Here's my big point. I know I ended on this yesterday as well, but let me try to make it more explicit now. I'm saying we check our solutions by taking derivatives. We took two derivatives here and found if we use x equals x naught cosine omega t, if we take two derivatives, indeed, we will find that the second derivative of x with respect to t does equal negative times a constant times the original x. Our original differential equation said that constant was supposed to be k over m. I mean, that's just a constant, and omega squared is just a constant. So what we did worked. We got a negative sign times a constant times the original x. It works as long as omega squared, sorry. As long as omega squared is just another name for the same constant as k over m. As long as they are the same thing, then our solution does satisfy the differential equation. So first of all, that means our solution does work, and we're going to use it for the rest of this course. But also, and I know we have 2 minutes left, this is my last page. First of all, then, our conjecture for cosine does work. It does solve the diffie-q. But second of all, most importantly, and this is like the last punchline of the last minute, that means the mass oscillates at a rate that is fixed by k and m. Like, in the end of the day, we learned two things. One, the solution works as long as by omega squared, we mean k over m. But two, oh my God, if omega squared equals k over m, Or in other words, if omega equals square root of K over M, what we're saying is that the rate at which this thing goes back and forth, the rate at which this thing cycles back and forth is fully determined, fully fixed by how heavy the mass is and how stiff the spring is. What will be known next week as parameters of the system, as opposed to what it's not at all determined by, what doesn't matter at all, is how far out we started it. Like notice there's no x naught in the omega expression. Omega is fully fixed by the mass of the spring and the stiffness of the spring, the ingredients of the system that you can know before you even set it up. It's not at all determined by how you set it up. That's what this is saying. So that's the conclusion. And hopefully that will help somewhat with, go back to math 2, homework 2, et cetera, et cetera. So we're done. Have a great weekend. I'm just going to hang out for a second if there's any questions, but I'm turning off the recording, and have a great weekend, everybody.